Hey everyone, and welcome to today's Explainer. If you're gearing up for your SMAW NC2 assessment, you already know the deal. The stakes are high. It's not just about laying down a decent bead in the shop, right? It's about proving absolute, total competence while an assessor watches your every move. Today, we're literally setting the stage to help you master that assessment. We aren't just going to look at the physical motions. We're going to unpack the invisible science behind a perfect weld. By the time we wrap up this explainer, you're going to know exactly what the assessor is hunting for, why the metal behaves the way it does, and how to prove without a doubt that you are a master of your craft.
Okay, let's dive into this. Our battle plan for today is pretty straightforward. We'll hit safety and setup essentials, equipment and polarity science, the step-by-step procedure, diagnosing defects and beads, and then finish up with passing the oral drill.
All right, starting right off with Section 1, Safety and Setup Essentials, the fatal errors that end your assessment.
Now I want you to imagine I'm your assessor for a second. I'm fair, sure, but I am absolutely strict. The very first thing I'm grading you on, it has nothing to do with your physical talent or how steady your hands are. It's all about the golden rule of the assessment. Remember this rule. A perfect-looking weld produced unsafely is still marked not yet competent. That is totally non-negotiable, guys. If you decide to skip throwing on your full PPE, the helmet, leather apron, safety shoes, gloves, even for just a super quick tack weld, boom, automatic failure. Safety isn't just a polite suggestion. It's literally the foundation of your competence.
So, we need to talk about the 4 primary hazards you absolutely must memorize. First up, electrical hazards. These bring a serious risk of shocks and burns. Then there's fire. Stray sparks hitting flammable materials can literally lead to explosions. Fumes are next, and those will cause severe respiratory problems if you aren't careful. And finally, radiation from the arc itself, which causes arc eye and nasty skin burns. Actually, here's a quick pro tip for you. Simply testing your helmet's auto-darkening filter before you even strike the arc can save you from severe radiation burns. Because if it doesn't darken fast enough, you're getting arc eye, even with the helmet down. Respect the hazards and protect yourself. Moving right along to Section 2, Equipment and Polarity Science, the invisible forces shaping your weld.
You see, a truly competent welder doesn't just pull a trigger and cross their fingers. They understand exactly why the metal is behaving the way it does under the intense heat of that arc. Take the heat-affected zone, or HAZ, for example. When you're welding, the area right next to your molten pool gets insanely hot, but it doesn't actually melt. This massive heat alters the metal's grain structure, which often makes the HAZ the absolute weakest point of your finished piece. Believe it or not, cracks actually start right here in the HAZ most of the time, not in the filler metal you just deposited. And that is exactly why your cooling rate and your travel speed are totally critical quality decisions. They dictate the structural integrity of the joint, not just how pretty the surface looks.
And this brilliantly illustrates how tweaking your machine settings alters those invisible forces. Think about direct current electrode positive, or DCEP, versus direct current electrode negative, DCEN. DCEP gives you much deeper penetration simply because 2/3 of the heat is concentrated right at the electrode tip. DCEN, on the other hand, gives you faster melt-off but way less penetration because the heat is focused down at the workpiece. So, those incredibly frustrating penetration issues beginners always have? A lot of times, that's just a poorly chosen polarity setting. If your weld looks great on top but just won't penetrate, you might literally just have your heat focused in the wrong place.
Now think about the number 70,000. In the super common E7018 electrode code, that 70 actually stands for 70,000 psi minimum tensile strength. But it's that 8 at the end that tells us this is a low hydrogen electrode. Assessors love this detail for oral questions. They want to know if you understand that an E7018 requires proper dry storage in a rod oven. Why? Because if that flux coating absorbs even a little moisture from the humid air, that moisture turns into hydrogen right in your arc. It gets trapped in the metal, and boom, you've got hydrogen-induced cracking. It's a real game changer.
All right, moving to Section 3, the step-by-step procedure, from raw material to inspection.
So let's move from the science side back into the physical execution. Remember, the assessor isn't just staring at your final product. They're watching your safety, your accuracy, and your technique across these 6 key steps. Let's move to and see how this builds. Preparing and cleaning, setting machines, tacking, completing the weld, removing slag, and finally inspecting. I really want to emphasize step 1 here. If you brush off the cleaning phase just because the metal, looks clean enough, you're leaving behind invisible surface oxidation or oils. That traps contamination straight into your weld pool, pretty much guaranteeing porosity and ruining your bead before you've even struck the arc.
When you get to step 4, completing the weld, you're basically juggling these 4 parameters all at once. Amperage is controlling your heat input. Arc length is your exact distance to the workpiece. Travel speed is your pace along the joint, and your electrode angle dictates how that heat distributes and how the penetration shapes up. To master the whole shebang, you really have to use your senses. For instance, a perfect arc length gives you that awesome, steady, sizzling sound, kind of like frying bacon. But if you pull back too far, making your arc length too long, you'll instantly hear this loud, erratic crackle. It's unmistakable.
Which brings us to Section 4, diagnosing defects in beads, reading the finished weld.
Here's the thing. Highly skilled welders, they don't sit around waiting for an inspector to tell them they messed up. They instantly read a bead to self-correct their machine settings or their hand movements right mid-weld. Let's break down the root causes behind some common bead appearances. If you're seeing a narrow, ropey bead with a high crown, you don't just have an ugly weld. You have a clear diagnosis. Your travel speed was way too fast. The arc just didn't dwell long enough to spread out and fuse properly. Or what if it's super spatter heavy and inconsistent? That means your arc length was wandering and it was definitely too long. Read the metal, guys. It tells you exactly what your hands were doing.
So the crucial point is, just think about how these major defects break down. Porosity, undercut, slag inclusion, cracks. Most of these absolutely terrifying defects easily trace back to just 4 basic things: incorrect amperage, poor technique, moist electrodes, or dirty materials. If you've got undercut just melting a massive groove into your base metal, drop your amperage or fix your travel angle. Understanding the specific breakdown is the difference between blindly guessing at what went wrong and surgically fixing your mistakes on the fly. And finally, Section 5, passing the oral drill, thinking under pressure.
Okay, so you've finished your weld, but the assessment is absolutely not over. The assessor is going to test how well you think on your feet under pressure. Let's simulate a rapid-fire drill to really test those contingency management skills. Here's your scenario. You're mid-weld. Suddenly, you notice excessive spatter just flying everywhere, and the sound totally changes to an erratic, crackling arc. What do you check first? Think about it for a second.
Stop and check your arc length. That loud, crackling arc almost always means you are just scattering heat and metal way outside the weld pool by holding the arc too far away. You don't just put your head down, keep going, and hope it magically fixes itself. No way. You stop, you adjust your distance, and you regain total control of your puddle.
Let's try another one. This is a classic trick question to test your professional integrity. Let's say your finished weld looks absolutely fantastic visually. Just beautiful ripples, zero spatter, looks ready for a textbook. But when you actually measure it, it's slightly undersized against the drawing specification. What is your decision?
It fails specification and must be corrected. You have to state this firmly and confidently to the assessor. An undersized weld simply cannot bear the structural load it was engineered for. Cosmetic appearance never ever overrides a hard, measured, dimensional requirement. A beautiful weld that snaps under pressure is, at the end of the day, a failed weld.
There's a saying that really summarizes the core philosophy of a master welder, and it's exactly what the assessors are searching for in you. Stop, identify the root cause, correct it properly. Rushing past a safety concern or trying to hide a defect under your next pass just so you can finish the job quickly is judged way, way worse than making the original mistake in the first place. They are testing your professional integrity, plain and simple.
And that brings us to our final provocative thought for this explainer. Do you actually understand why the metal behaves this way? Or do you just know how to lay a pretty bead? Look, anyone can get lucky with a steady hand on a good day. But a truly competent, certified professional, they know the science of the polarity, they know the exact root cause of a defect, and they stick to the rigid discipline of safety. So, mentally review the science we unpacked today. Step into that shop, look your assessor right in the eye, and show them exactly what you know. Keep learning, stay focused, and I'll catch you in the next explainer.